In this lesson, we're looking at solving systems of equations algebraically, and there are two main methods for solving these systems algebraically. The first of which is substitution, the second of which is elimination. We're going to look at substitution first. Basically, in substitution, since we have two equations, we're basically going to start off and we're going to solve one of those equations for a specified variable, really a variable of our choosing. So we're either going to choose x or y, and we're going to isolate that x or the y for that equation. All right, and so think about the result of that. If I were to take one of the equations and solve for x, I'll have x equals some expression. If I solved it for y, I'd have y equals some expression. So then we have an expression that's equal to either our x or our y, and we're going to take that expression and we're going to substitute it in to the other equation. All right, and that's what we're doing then in the second step. So again, we use one of the equations because we have two equations. If we solve one of the equations for one of the variables, so we get y equals an expression, and then we take that expression and plug it into the second of our equations, and then we solve what's left over, okay? So again, pick one variable with one of the equations, isolate that variable, get it by itself, solve for it, and then take the expression that that variable is equal to and plug it in to the second equation, all right? And then we solve what's left. For example, if I look at this first one, in this one, I want to isolate one of the variables, and the obvious choice here, what should be the obvious choice for the variable that I want to isolate, it's going to be the y value. And the reason for that is because y is already by itself. That first step is already completely done. Like if I look at this first guy, it says y equals, y is by itself, so y equals the 3x plus 4. So y equals this expression right here. All right? So if y is equal to that expression, I'm going to take that expression and I'm going to plug it in for y in my second equation. All right, so let me take that second equation, which was y equals 4 plus x. But instead of y, whoops, I erased a little more than I wanted to there. But instead of y, I'm going to plug in that expression. So right here, instead of y, I'm going to have the 3x minus 4. All right, so I'm plugging that expression in for y in my second variable, or in my second equation. And now I want to solve this for x, because that's all I have left. So I solve the way I would normally solve an equation. I subtract the x from each side. I get 2x minus 4 equals 4. I'm going to add the 4 to each side. So when I do that, I'm left with a 2x equals 8. And then I divide by the 2. So I find out that x equals 4. And that's great, but I'm not done yet. This is a system of equations. I need an x and a y value for my answer. I only have the x value, so I've got to plug this back in. And I can plug it into any one of these equations that I had. I'm going to plug it into the second one just because it looks a little bit easier. So I end up with y equals 4 plus x, which was also a 4. So I get y equals 8. And that's it. And I can write my answers in ordered pair, and that would be fine. If you leave it as x equals 4, y equals 8, that would also be fine. And the other thing I should mention about these is that I can easily check my solution and be 100% sure that I have the right answer simply by plugging those values in, just like we've done previously. You can test a point by plugging it in and see when it works for all the equations. Okay. When I look at the next one I want to isolate one of the variables, and so I scan down through here, and the obvious choice should be the x. All right. If I solve for the x in the second equation, because when I look at this x value in the second equation, it's practically by itself. It doesn't have a coefficient other than the 1 that's there, so it's practically by itself. The other okay option would be the y in the first equation. The only reason I avoid the y in the first equation, it kind of looks like it's almost by itself, but because that negative's in front there, it doesn't make it quite as good of a choice as the x value in the second equation. So I'm going to take this x value and get it by itself, so I'm going to subtract the 4y from each side. And when I do that, I find out that x equals, let me give a little more space here, I find out that x equals, that's going to give me a negative 4y plus 11. And now I have an x value. This expression is my x value. X is actually a negative 4y plus 11. So I'm actually going to plug that in for the x in my first equation. So I come back up to this first equation. I had 3 times x minus y equals 7. But instead of x, I'm going to plug in the expression that x is equal to, the negative 4y plus 11. And now I just have to solve this thing. So here I'm going to distribute the 3. That's going to give me a negative 12y plus 33 minus y equals 7. And now I'm going to combine the like terms here. So I've got like terms, the negative 12y and the negative 1y. That gives me a negative 13y plus 33 equals 7. I subtract the 33 from each side. So I get a negative 13y equals a negative 26. I divide each side by the negative 13. And I find out that y equals 2. But once again, I'm not done yet. I have to plug this back in. So I need to decide, am I going to plug it into the first equation, the second equation, or the third equation? And the initial thought there is, well, there is only two equations. I had one initial equation, a second initial equation, but I wrote a third equation that's already solved for x. And so with substitution, what's really nice here is I can plug it into that third equation that's already solved for x. X equals a negative 4 times y, which is 2, plus 11. And now it's already solved for x. I just have to simplify. That gives me a negative 8 plus 11, which is a positive 3. And once again, I can express this as an ordered pair. That would be 3 comma 2. If you just leave it as x equals 3, y equals 2, that's fine as well. All right? When I take a look at the next one, either one would be a good candidate for this one, either solving for x or solving for y. I'm going to go ahead and solve for x in the second equation just because it's more readily available for me. So I'm going to subtract the 3y from each side. That doesn't look like a y at all. Let me try that again. There we go. And so I find out that x equals, that's going to be a negative 3y plus 13. And now from here, I've got to go ahead and plug that thing in to my first equation. So I take my first equation, which is this guy right here. I'm going to plug that value in. So I had 2 times x plus y equals 11. But instead of the x, I'm going to plug in the negative 3y plus 13. So I substitute that expression in, and now I simplify. I solve. So I distribute. That's going to give me a negative 6y plus 26 plus y equals 11. I combine like terms. So that's going to give me a negative 5y plus 26 equals 11. I subtract the 26 from each side. So I get a negative 5y equals a negative 15. And now from here, I just have to divide by this negative 5. And I find out that y equals a positive 3. Once again, I'm not done yet. I have to plug it back in. I can either plug it into the first equation, the second equation, or this third equation that I came up with. Since the third equation is already solved for x, I'm going to plug it into the third one. Whoops, that is a 3. Let me try again. And so when I do this, I get negative 9 plus, sorry, that's a 13. Negative 9 plus 13, which is 4. And so my solution here is 4 comma 3. And that's it. And again, we can plug this back in and check it to make sure it works. If I look at this one, as soon as I take a look at this thing, I'm trying to decide whether I want to isolate x or y, and really nothing looks like a good option at this point, part of which because we look at this thing and we're already annoyed because there's a fraction in it. So let's do one extra step. Let's get rid of the fraction. So I'm going to get rid of the fraction by multiplying this entire second equation by 2. Remember, with equations, you can always get rid of the fractions by multiplying through by the common denominator. So this second equation becomes an x minus 2y equals 36. And now when I look at the easiest variable to solve for, it becomes obvious. I'm going to solve for this x in that equation that I just modified. And I'm going to find out that x equals a 2y plus 36. And now from here, I got to plug that back into this this first equation. So I'm going to plug it into this first equation. That's going to give me a negative x plus 2y equals 8. But instead of x, I'm going to plug in the expression that I just found, the 2y plus 36. And when I do that, I have to distribute this negative. So I'm distributing the negative. That's going to give me a negative 2y minus 36 plus 2y equals 8. From here, I have to combine the like terms. So I'm going to combine like terms, the negative 2y and the positive 2y. Those cancel out, so I'm just left with a negative 36. Over here, I still have the 8. So what I end up with is something that says negative 36 equals 8, which I know for a fact is ridiculous. So I'm going to say that those do not equal one another, which means this one's actually no solution. Okay? When I get a false statement like that, it means that there's no solution for this one. Okay? With elimination, what we want to do is we want to write each equation in standard form. And really, when we say that, what I really mean is standard form in quotations. I want it close to standard form because essentially what I need is for my x values, my y values, my equal, and my constant values all to line up. All right? And if I used another format like y equals mx plus b, well, then it would be silly to do elimination because substitution would be such an easy option. All right? So we kind of want it in standard form. We don't have to worry about some of the specifics on standard form, like not having fractions or not having a negative a value or not having a common factor between the three values. We don't particularly care about that. What we care about is the order, x, y equals constant, okay? Because we need everything to line up. Then what we're going to do is we're going to multiply the equations so that the coefficients of one of our variables become additive inverses. And that word additive inverses essentially means two numbers that when added together equal 0. So like -5 and +5, or -3 and +3, or +10 and -10, or +7 and -7, all right? Values that when added together give me negatives. So we're either going to multiply one or both equations by something so that we get those kind of values in front of either x or y. So I need additive inverses in front of my x or in front of my y. All right. Once I have additive inverses, I just add the two equations together, and this is why we needed everything lined up. I add the x to the x, the y to the y, the constant to the constant, and I just solve whatever's left after I add those equations together. Okay. For example, if I look at this first one, I have to decide: do I want to get additive inverses in front of the x, or do I want to get additive inverses in front of the y? I have to pick a variable to get additive inverses in front of. And the obvious choice here is the y values. And the reason for that, when we look at the values here, this is actually a 1. So I have a -1 in front of one of the y values. I have a +1 in front of the other y values. Those are additive inverses. So I already have step 2 done. These are additive inverses. So I go right to adding these together. All right. And so that's why I want to look at this and I try to choose what's best. So here I'm going to add these together. When I add them together, I end up with a 5x. Here the y's eliminate. They give me a 0. That's why it's called elimination. Over here, 2 plus 8 gives me a 10. And now I solve the equation that's left is 5x equals 10. I divide each side by the 5. And I find out that x equals 2. So now from here, I just have to plug this thing back into my equation. It doesn't matter which one I plug it into, whichever one looks easiest to you. I'm going to plug it into this second one. So I do 2 times x, which is the 2, plus y equals 8. And now I just have to simplify this and solve. That's going to give me a 4 plus y equals 8. And now from here I have to subtract the 4 from each side. And I find out that y equals 4. So I get this ordered pair. Again, I can express as an ordered pair, 2, 4. And that's it. All right. If I look at the next one, I have to decide which variable I want to get additive inverses in front of. Really here, it's not that obvious. You could get additive inverse in front of x or y. It doesn't matter. For our purposes, we'll get in front of y this time. And the only reason I'm choosing y is because I've got one that's positive and one that's negative already. Okay, so I don't have to worry as much about the sign. So the first one, and this is kind of like getting common denominators. This guy has a y value of -1, the other one is a 4. So it's like getting common denominators. I'm looking for the least common multiple, which between a 1 and a 4 is a 4, so I have to multiply the first equation by 4, and the second equation essentially by 1, which means I don't have to change anything. So this first equation becomes an 8x minus 4y equals 28. And as I look at this, I've got a positive 4 and a negative 4. If I happen to multiply these and I get a positive 4 and a positive 4 in front of my y values instead of additive inverses, all I have to do is multiply one of the equations by -1 to make them opposites. And that's really what I want so that I can add these together. Okay? I can subtract equations, but we tend to make sign errors when we do that. So I would stick to getting additive inverses so that you're always adding for that consistency. And now I add straight down a 1x plus 8x is a 9x. The y values eliminate one another, and then 17 plus the 28 gives me a 45. And then from here I'm going to solve this. I divide each side by the 9, and I find out that x equals 5. But I'm not done yet. I have to plug this into one of my equations. I'm going to choose the first equation. I could have used, the second equation. I've got the first equation, the second equation, or even this third equation that I've created. But the second one seems to be the best option here. So I'm going to plug it into the second one. So I plug the 5 in for x, and I'm going to be solving for y. And so from here, I just have to subtract the 5 from each side. So I end up with 4y equals 12. and then I divide by the 4. So I find out that y equals 3, and that's it. I've got my answer here, the 5, 3, and I'm done. All right? If I look at the next one's a little bit tricky. I want to decide, do I want additive inverses in front of x or in front of y? And really, neither of these are great options this time. So I'm going to go with the x only because it's got smaller numbers here. So again, when I look at this, it's almost like getting common denominators. I'm looking for the least common multiple between 2 and 3, and the least common multiple here is 6. So in order to turn that first equation, that first value into a 6, I have to multiply it by 2. So I multiply that entire first equation by 2. The second equation, if I want to turn that 3 into a 6, I have to multiply it, I have to multiply that first equation by 3. Let me try that again. And I have to multiply the second equation by 2. Okay, so again, it's very similar to what we do when we're getting common denominators. But now, when I look at this, I'm going to get a positive 6 in the numerator, I'm going to get a positive 6 in the denominator. In order to tweak this just a little bit, I just have to make one of these a negative 6. So in other words, I have to multiply one of these by a negative, and I'm going to choose the 2. So I'm going to make the 2 a negative when I multiply. That 2 over here got a little bit ugly, so I'm going to just rewrite it a little bit. And so now the result is this first equation becomes a 6x plus 15y equals 3. The second equation becomes a negative 6x minus 14y equals a negative 4. So what happens here is I get that positive and negative like I wanted, and now I add these together. All right? So I add them up. That's going to give me a 1y, or just y, equals a negative 1. And now from here, I've got to plug this into one of the equations. I'm going to plug it into the first equation. That seems like the easiest one to plug it into. So I do the 2x plus 5 times y, which is the negative 1, equals 1. And now I have to solve. That's minus 5. I have to add the 5 to each side. So I find out that 2x equals a 6. And then from here, I just have to divide each side by the 2. And I find out that x equals 3. Okay, so I get this ordered pair, 3, negative 1. It's just a nice way to express my answer. All right? In this last one, I just have to get additive inverse in front of one of these, and as I look at this, neither one looks like a great option right now, just because I'm dealing with a fraction again. So the first thing I'm going to do, even if it takes an extra step, I'm going to get rid of the fraction. So I'm going to multiply this second equation by 2, just so I can get rid of that fraction. And so what happens is my first equation doesn't change, the y plus 2x equals 8 doesn't change. That second equation now becomes a negative y minus 2x equals a negative 8, which actually works out really, really well for us because now I automatically have additive inverses. Now that won't happen every time, but it's always good to get rid of the fraction and then see what you're dealing with. So now I have additive inverses already, so I'm going to add these up. Make sure these don't get mixed up. When I add these up, over here the y's cancel out, but the x's also cancel out, so I'm left with nothing. I'm left with 0. Over here, 8 plus a negative 8 is also 0. So I get 0 equals 0, which is a true statement. Well, unlike when I get a false statement, I know it's no solution. But when I get a true statement, this is a situation where I have infinitely many solutions. So I'm going to say infinite. There's an infinite number of solutions here. And keep in mind, I don't just say all real numbers because that implies any values that I want for x and any values I want for y. I say there's an infinite number of solutions. In other words, there's an infinite number of very specific ordered pairs that will work for this one. Because what I had really was the same equation twice. Okay? So any ordered pair that works for one also works for the other. So I have an infinite number of solutions. Okay?